Welcome, curious minds, to another expedition into the fascinating world of numbers and the surprising ways they connect everything.
It's true. Numbers really do seem to pop up everywhere.
They really do. Numbers often feel like this universal language, but sometimes they whisper secrets about connections we just never expected.
Exactly.
And today, we're taking a deep dive into one of those secrets, hidden within, well, a truly incredible resource for anyone fascinated by patterns. The Online Encyclopedia of Integer Sequences, the OEIS.
Ah, the OEIS, yes. It's quite something.
Think of it as like the ultimate library for numerical patterns, right?
Yeah.
Where every sequence tells a story.
It's definitely more than just a collection. I'd say the OEIS is a living archive. It compiles sequences from, well, every corner of mathematical inquiry and often reveals these profound links between fields that seem, totally separate.
Right.
It's where a lot of mathematicians first stumble upon patterns that spark deeper questions or connect different research areas they're working on.
Okay, so our mission today then is to unpack one very specific, very intriguing sequence, a perfect example of this interconnectedness you're talking about. OEIS A800260.
Oh, good one. A000026.
We're going to explore its many initial definitions, discover its truly surprising appearances across diverse scientific and mathematical domains, and really try to understand why it matters, to everyone from pure mathematicians to computer scientists and even theoretical physicists.
It certainly has a wide reach. At its core, A800260 counts some very specific combinatorial objects.
Okay.
The OEIS entry, it starts by defining it as the number of rooted simplicial 3 polytopes with n plus 3 nodes.
Whoa, okay. Nodes.
It also describes the rooted 3 connected triangulations with 2n plus 2 faces, and equivalently, the rooted 3 connected trivalent maps with 2n plus 2 vertices.
Right.
These are all deeply related concepts in graph theory and geometry.
Okay, my brain just did a little zigzag there with those terms. Before we untangle what all those mean, let's get a concrete sense of the numbers themselves. What are we looking at?
Good idea. So the sequence starts for n0 with 1.
Okay.
Then for n1, it's 1 again. Then 3, 13, 68, 399, 25, 30.
Wow.
1c9, 65. And it just keeps growing pretty rapidly.
Yeah, you see those numbers and you immediately wonder, what kind of growth is this? And what intricate structures are they actually counting?
Precisely.
So let's unpack this. We've got rooted simplicial, 3 polytopes, triangulations, trivalent maps. These terms sound incredibly specific, almost like, mathematical jargon.
They can seem that way at first.
For someone like you, maybe a number theory student listening in, what are we actually counting here, fundamentally?
Yeah.
What do these objects represent in a way that helps us maybe visualize them?
That's an excellent question. And it gets right to the heart of combinatorics, which is all about counting arrangements and structures.
Okay.
So when we talk about these objects in the context of A000260, we're essentially looking at different ways to count certain types of, let's say, geometric or graph theoretic shapes.
Shapes, okay.
A 3 polytope is basically a 3-dimensional solid with flat faces. Like, imagine a perfectly formed gemstone.
Right.
Simplicial means all its faces are triangles, the simplest possible polygon.
Okay, like a diamond where every single facet is a triangle.
Exactly like that. And the rooted part is crucial. It's about unique identification.
How so?
Well, imagine you have many identical diamonds. If you pick a specific corner or edge on each one and say, mark it, suddenly each diamond becomes unique for counting purposes.
Ah.
It prevents us from double counting rotated versions of the same object. Gives each structure a unique orientation or a starting point, if you will.
Got it. And the other terms? Triangulations, trivalent maps.
Right. Triangulations often refer to graphs drawn on a plane where every enclosed space, every face is a triangle, and trivalent maps. Well, those are graphs where every single point or vertex has precisely 3 lines, 3 edges connected to it.
3 lines coming out of every dot.
Exactly. And what's truly fascinating here is that even though these definitions describe, visually distinct things or structural properties, they all lead to the exact same sequence of numbers.
That's wild.
It's a common and frankly beautiful phenomenon in combinatorics.
Okay, here's where it gets really interesting, for me anyway. This sequence isn't just stuck in those initial geometric definitions, right?
Not at all.
It pops up in so many different contexts. Like the OEIS entry also describes A000060 as the number of rooted loopless planar maps with n edges.
Yes, that's another key one.
My first thought was, how on earth do these geometric shapes connect to something called a planar map? Can you maybe help us visualize that jump, maybe with one of those small numbers, like the 3?
Certainly, a planar map is just a graph you can draw on a flat surface like paper without any edges crossing each other.
Okay, no crossing lines.
And loopless means no edge connects a vertex back to itself. So for N2 edges, the OEIS explicitly tells us there are A2 such maps.
3 of them. What do they look like?
Imagine them like this. 2 of them are what we call rooted paths. Picture 2 dots with 2 lines connecting them in sequence, like a little zigzag. Dot line, dot line, dot line. But you have to choose a root, say one end.
Okay, 2 paths.
And the third map is a diagon. Think of 2 points connected by 2 distinct edges. It forms a kind of lens shape between the 2 points.
Ah, okay, like 2 rows between the same 2 towns.
Exactly. So you have the 2 paths and the 1 diagon. That's 3 structures. And even these simple things, which look very different from a 3 polytope, give us that same number, 3 for N2.
Wow, okay. That really shows how different things can lead to the same count.
It's a powerful illustration, yes, how diverse combinatorial objects can be counted by the same sequence.
And the connections deepen even further. It's also the number of intervals in the Tamari lattice. Wait, rotation lattice of binary trees of size ni. What is a Tamari lattice? And why would intervals within it give us these same numbers? This is like finding the same pattern in completely different kinds of fabric.
That's a perfect analogy. Tamari lattices are these elegant structures that arise from operations on binary trees.
Binary trees.
Can please.
Computer science again.
Often, yes. Think of a binary tree, like a family tree, where each person has at most 2 children. You can perform specific operations called tree rotations that basically rearrange the branches of the tree while preserving its underlying structure.
Okay, shuffling the branches around.
Right. A Tamari lattice organizes these trees based on whether one can be transformed into another through these rotations. An interval in this lattice is essentially a pair of trees, say XY, where tree X can be transformed into tree Y through a sequence of these rotation operations.
So like a path between 2 tree structures in this lattice.
Precisely. And the fact that counting these intervals, these paths, turns out to be equivalent to counting the polytopes and the planar maps, well, it highlights a deep structural relationship. It's like discovering a blueprint for, I don't know, a bridge can also be used to understand the structure of a complex database, just by changing the context.
That's amazing. Okay, the journey continues. We also see A800260 listed as counting. Get this. Uniquely sorted permutations of 2n's plus 1 that avoid the pattern 231, and also the number avoiding 132. This hints at permutation patterns, which seems like a whole different world from shapes and trees. How does a sequence about polyhedra connect to arrangements of numbers?
Yes. This is a classic example of bijections in combinatorics, and it's often a core aha moment for students, especially in number theory or related fields.
Bijections, like a perfect pairing.
Exactly. A bijection is a one-to-one correspondence, a perfect matching between the elements of 2 different sets. In this case, it means there's a mathematical way to map every rooted simplicial 3 polytope to a unique Tamari lattice interval, and also to a unique permutation of a certain type that avoids specific patterns like 2n31 or 132.
So there's a direct translation between them.
There is. The existence of these bijections is profound. It tells us that these different objects, despite looking completely different, having totally varied descriptions, they possess the exact same underlying combinatorial complexity.
It's not just a coincidence the numbers match.
Not at all. It means there's a fundamental, almost you could say Platonic structure that these diverse objects are all just different manifestations of.
Huh. Like finding the same musical chord played on a piano, a guitar, and a cello.
That's a beautiful way to put it. They sound different, maybe, but the underlying harmonic structure is identical. These bijections reveal that common structure. It suggests the universe of mathematical forms might be far more unified than we often perceive.
Wow. Okay. This sequence really casts a wide net. I mean, I've seen it linked to planar maps, Tamari lattices, and Lambda calculus through Noam Zalberger's work. What exactly is Lambda calculus, and how does the sequence bridge such diverse areas like pure math and theoretical computer science? My brain just did another little flip there.
It's a common brain flip, don't worry.
Yeah.
So Lambda calculus is a formal system. It's foundational to the theory of computation and programming language design.
Okay, so important for computers.
Very. It's a way to describe computation based purely on function abstraction and application applying functions to arguments. It's crucial for understanding how programming languages fundamentally work.
Then A000260 fits in.
How? The connection, as explored by researchers like Noam Zeilberger, reveals that these fundamental combinatorial structures, like the ones counted by 000260, aren't just abstract mathematical curiosities. They actually underpin the very logic and structure of computation itself.
So the patterns in the sequence reflect patterns in computation.
In a deep sense, yes. This kind of unexpected connection across fields like graph theory, combinatorics, and theoretical computer science often reveals these deep, unifying mathematical principles. It shows these aren't isolated subjects.
Okay, and get this. A00260 even shows up in integral geometry, namely in the algebra of unitarily invariant valuations on complex spaceforms. That sounds incredibly abstract. What does it even mean for a counting sequence to appear in such a high-level geometric context?
It is indeed a sophisticated connection. It bridges these discrete counting problems with continuous, highly symmetric spaces. Integral geometry basically deals with measuring geometric properties of shapes and spaces.
Measuring shapes, okay.
And valuations are a specific, consistent way of assigning a size or measure to these shapes. When we talk about unitarily invariant valuations on complex spaceforms, we're deep into advanced geometry and topology, dealing with complex spaces that have a particular kind of symmetry.
So very advanced geometry.
Right. For a combinatorial sequence like A000260 to emerge here, it means that these discrete counting problems at some fundamental level are also describing properties of continuous geometric spaces. Imagine you're counting, apples. And that exact same number pattern turns up when physicists are calculating the shape or volume of something incredibly abstract and smooth, like some bendy, multidimensional surface in theoretical physics.
That would be weird.
It implies a profound underlying mathematical consistency. It shows how numbers really are universal, bridging the discrete and the continuous.
What about more tangible applications? I saw a reference to architectural applications of graph theory connected to this sequence. How does A000260 relate to architecture? Are we counting blueprints here or something?
It's definitely more abstract than counting blueprints directly, but it's still relevant in a way. A000260 itself isn't directly counting unique building designs.
Right.
But the principles it embodies, the deep combinatorial structures it represents, those are the same kinds of principles that underlie how we model relationships in architecture using graph theory.
Okay, so it's about the underlying math tools.
Exactly. Graph theory in general lets architects and urban planners model things like spatial relationships, connectivity, flow within buildings or city layouts, designing efficient corridors, optimizing room arrangements, analyzing structural integrity.
That makes sense.
These can all involve graph theoretic principles. The fact that A000260 arises from fundamental combinatorial graph structures suggests that the principles it embodies could, in some abstract way, underpin the mathematical tools used to analyze and design physical spaces. It highlights how these abstract math concepts can have very practical, even aesthetic implications down the line.
And finally, a truly surprising connection. This one kind of sends shivers down my spine.
Yeah.
This sequence appears in theoretical physics, specifically mentioned in the context of a non-abelian analog of dBi from TT-bar. How does something so abstract from combinatorics connect with, the fundamental forces of the universe?
This is really cutting-edge stuff, often involving quantum field theory, string theory, attempts to describe the universe at its most fundamental level.
The really small or really high-energy stuff.
Precisely. dBi refers to the Dirac-Born-Infeld action, which is important in describing D-branes in string theory. T-bar deformations are a relatively new way to modify quantum field theories, and they've shown unexpected connections to gravity and holography.
Okay. Still very abstract.
It is. The appearance of a combinatorial sequence like a 000260 here suggests that the underlying structures counted by this sequence might be deeply embedded within the mathematical framework used to describe these fundamental physical phenomena.
So the sequence is part of the math that describes reality.
It's not uncommon for fundamental combinatorial objects to underpin models in theoretical physics. Imagine that the universe at its most basic level, described by string theory or something similar, needs a certain kind of mathematical building block. It turns out that these very numbers, the A000260 sequence, might be counting those building blocks.
Yeah.
Showing up as coefficients, maybe, or describing structures in the equations that aim to describe reality itself. It's like finding a specific prime number repeatedly appearing in the fundamental laws of physics. It hints at a deeper underlying code.
That's incredible. So we've seen these numbers and where they show up, but how do mathematicians actually work with them? It's not just counting on your fingers, right?
Definitely not for these numbers.
I see these incredible formulas in the OVIS entry. How do these help us understand A800260 in a deeper way, beyond just getting the next number in the list?
That's where the real power of mathematical formulation comes in. These sequences aren't just lists. They're governed by elegant rules and relationships.
Oh, okay.
When we have an explicit formula, like an equals 2 for n plus 1, n plus 1, 3n plus 2.
Whoa, factorials everywhere.
Yes. Or the slightly more compact an equals binomial 4n plus 1, n plus 1, 9 binomial 4n plus 1, n 1. These allow us to calculate any term directly, no matter how far down the sequence it is. We don't need to compute all the previous ones.
So if I wanted 100, I wouldn't have to list out the first 99 terms. I could just plug 100 into the formula.
Exactly. It's like having a direct phone line to the number you want.
Nice. What else?
Then we have recurrence relations. These are like a recipe where each step depends on the last one, or maybe the last few.
Like Fibonacci, each number is the sum of the previous two.
Similar idea, yes, though often more complex. For A00260, there's a definite recurrence relation, 3n plus 2, 3n plus 1, n plus 1an, 8, 4n plus 1, 2n1, 4n1, an1 equals 0. Looks messy, maybe.
A little.
But these are incredibly powerful for computational mathematics and also for proving properties about the sequence itself.
And I saw something about generating functions.
Ah, yes, generating functions like gf to gg2, where g was 1 plus xg4. These look complex, but they essentially encapsulate the entire infinite sequence into a single elegant expression, usually a power series.
The whole sequence in one function.
Exactly. It's like having a compact code or a seed that contains all the numbers in an infinitely unfolding pattern. Very powerful tools. And finally, for understanding the long-term behavior, especially for very large n, we use asymptotic formulas.
How fast does it grow? That kind of thing.
Precisely. For A000260, it's approximately an to OENN plus 72, R 52, 3m plus 52. This tells us the growth rate, it grows exponentially, quite fast. This can reveal a lot about the inherent complexity of the objects being counted.
So it grows really fast.
Very fast. And sometimes there are even integral representations, like one by Carol Penson mentioned in the entry. That's another beautiful way to define the sequence, bridging discrete numbers with continuous mathematics with calculus. These different formulas are the mathematician's toolkit for dissecting, predicting, and understanding these numerical patterns.
We really can't talk about the OEIS without acknowledging its founder, N.J.A. Sloan. He's listed as the author of this sequence, right?
Absolutely. Neil Sloan's dedication to creating and maintaining the OEIS has provided an absolutely invaluable resource. It connects mathematicians, computer scientists, physicists, researchers worldwide. It's hard to overstate its impact.
And a lot of the foundational work, especially on the planar maps part that this sequence relates to, comes from mathematicians like W.T. Tute.
Oh yes, William T. Tute. His pioneering work in enumerative graph theory, particularly his enumeration of planar maps and triangulations back in the mid-20th century, that really laid much of the groundwork for understanding sequences like A000260.
He figured out how to count these things first.
He developed fundamental methods. His contributions established a deep mathematical framework that still influences research today in combinatorics, graph theory, and beyond. He really provided the roots for many of these fascinating problems. His detailed enumerations and techniques are still widely cited.
So, wow. We've taken a truly remarkable journey today, haven't we?
It feels like it, yes.
We started with OEIS A800260, a sequence that, initially counts these very specific geometric structures, rooted simplicial of 3 polytopes, planar maps.
Things you can almost draw or visualize with some effort.
Right. But then we watched it just expand, showing up in the abstract world of Tamari lattices, relating to binary trees.
And connecting to the order of permutation patterns, which feels quite different.
Totally different. And even linking with foundational concepts like lambda calculus and computer science.
Yes, and we saw its surprising relevance in integral geometry, exploring properties of geometric objects in higher dimensions. That was quite a leap.
And maybe the most astonishing leap, its appearance in cutting-edge theoretical physics, hinting at these fundamental connections within the very fabric of the universe itself.
It really covers a lot of ground.
So what does this all mean for you listening in, the curious learner, the number theory student? I think it's just a fantastic example of how seemingly abstract mathematical sequences are profoundly interconnected, revealing this hidden unity across disciplines that, honestly, you might never expect. It's not just about finding interesting numbers.
No, it's about discovering the underlying language, maybe, the structures that connect these disparate fields. It shows that the work mathematicians do, whether they're counting discrete things or exploring continuous spaces, is often linked by these fundamental number sequences.
They're like threads weaving through the tapestry of math and science.
That's a good way to put it. Universal blueprints for complexity, perhaps.
This deep dive into A800260, it really shows us that the world of mathematics isn't just a collection of isolated islands. It's more like a vast, interconnected ocean, right? With powerful currents flowing between shores that look really far apart.
That's a very apt metaphor.
So it makes you wonder, what other surprising connections might be hiding in plain sight, just waiting for us to uncover them in the OEIS? How might these abstract ideas, these sequences, underpin the next big breakthrough in a field you'd least expect, maybe even one you're studying right now?
It's a tantalizing thought, and I really would encourage you, if you're interested, to explore the OEIS yourself. Pick a sequence that catches your eye. See where its comments and links lead you.
Yeah.
You might find your own fascinating bridges between different areas of knowledge and really experience that deep interconnectedness of mathematics firsthand.
Exactly. The adventure truly begins when you start looking. Until next time, keep diving deep.